Okay. So solutions to separable equations. So these first, we're going to do several examples through 1 to 12. We find the general solution of the indicated differential equation. And then we find an explicit solution if it's possible, but most cases we won't really find it. I'll just do we'll find a solution, go from there. But it just depends. The solution at the end will be what we have. So these are separable equations. That's all that we're focused on right now. Y prime equals x times y. The main deal with separable equations is you turn y prime here when we have it just on one-sided equation. We can turn it into dy dx. Or we can have dy dt in some cases, but it's y and x are the variables here. So y prime equals x times y becomes dy dx equals x times y. Then we put y, the variable y, and dy on the variables involved in y. On the side was dy, and the variables involved in x and dx on the same side. So you get like a normal integration. We have them on the same side. And we integrate both the left and right side after that. So we have dy over y and x dx. We integrate both sides, and we basically have 1 over y dy equal to integral x dx. And 1 over y is just the natural. When you integrate that, 1 over y dy just becomes ln y, absolute value bars. Very important here. And you have plus c1, constant from that, and then equals x squared over 2 plus c2. And these are both different constants. Okay, constant 1 and constant 2. Here's something that happens now. So we have ln y, the absolute value saying equals x squared over 2 plus c2 minus c1, because we subtract c1 from each side. Well, c2 minus c1 is just another constant. If we subtract a constant from a constant or add a constant to a constant, it's going to be a constant. 5 plus 6 is 11, which is a constant. 5 is a constant, 6 is a constant. We have 10 plus 20 is 30, all constants. And so it doesn't matter. And that's a very useful property for simplification. So it becomes ln y with absolute values as written is equal to 1/2 x squared plus c. And because I put 1/2 in front from x squared over 2. And that's because the integral of x dx is just x squared over 2, because you have x to the 1 power. So you do 1 plus 1, so it's x to the 1 plus 1 power divided by 1, the power plus 1, you know. So it's 1 plus 1 is 2, so it's x squared over 2. Just as a quick refresher. But we basically cancel out the natural log by raising both sides to e, the natural exponential thing. So we get the absolute value of y equal to e to the 1/2 times x squared times e to the constant c. But first we just have it plus. But that's the property of exponentials, is when you have addition, you have this like 1/2 x squared plus c all in the exponential, one thing. It can become e to the 1/2 x squared times e to the c. And we can also write e to the c as another constant. And we'll just call it c again, because really these are just constants. Unless the professor is extremely picky, it doesn't matter. We can just, for now, just use that. And when we get this, so we have absolute value of y equals c times e to the 1/2 x squared. And we can get rid of absolute values and make it plus or minus c on that side. So the right side becomes just plus or minus constant c times e to the 1/2 x squared, because absolute value can be plus or minus and all that. Cancel it out. So positive constant is a negative constant. They're just constants at the end of the day. Like -1 times c is c, because -1 times 2 is -2, but it's still a constant. It's something to consider with constants, how things work out. So it's y. So you could also do a times e to the 1/2 x squared instead of c. You could do a, but that's how you simplify this down. So y of x equals a times e to the 1/2 x squared is the general solution. A is just a constant, but we could use anything to do, a, c, Generally a capital letter though. I use C1, C2, C, and A basically. All constants in this one. Really up to discretion of professor and everyone, but the main point is that your work makes sense. So, furthermore, after all that, we're going to do a lot of examples just because it's a good review of your Calc 1 and 2 skills as well. I'll have the integration method. So, your earlier calculus skills. And I think I wrote it out pretty simply, so it continues on here. So this one is very similar. It's xy prime equals 2y. So x times dy dx equals 2y, and you separate them out. You divide y and you divide by x on both sides, and you divide by y on both sides. So that's why it's dy over x equals 2x divided by x dx. And especially when we're having stuff, you want to keep y somewhat simple because of how, especially when you have the absolute values and stuff. So again, this is very similar to how when you eventually get a case where you get absolute value of y equal to e times c times m. But it's the same type of problem, and I think it's fairly obvious, especially in one like this. And I even made a note that a equals plus or minus e to the c power, pretty much. Again, there's different ways to do all this, but it just becomes y of x equals a times x squared. It's a general solution. That's a general solution again. Number 3 is again very simple or similar. It's y prime equals e to the x minus y. But this time I write as dy dx equals e to the x over e to the y, because you can split that up. When you have an exponential and it's raised to subtraction between them, you can do division, separate them. E to the x divided by e to the y, and that makes it that makes us allowed to separate very easy. So we multiply e to the y. We multiply both sides by e to the y and get dx by itself, so we basically separate the variables. And so e to the y dy equals e to the x dx, and you integrate both sides. E to the y plus c1 equals e to the x plus c2. You simplify down to e to the y equals e to the x plus c. Then we take the natural log this time instead of both sides and get y equals ln parentheses e to the x plus c. So it's just y of x equals ln parentheses e to the x plus c. That's the general solution there. Still on the same process, so we have y prime equals 1 plus y squared all times e to the x. We do dy dx to get dy dx equal to 1 plus y squared e to the x. And we divide by 1 plus y squared. And this is an interesting one. So we have e to the x on that side, so dx. So the integral of 1 over 1 plus y squared dy equals integral of e to the x dx. But we'll recall a certain rule from calculus, from earlier calculus. The integral of 1 over 1 plus t squared or 1 plus x squared, and then you have the dx or dt depending on the variable, is equal to the inverse tangent of the variable. So the inverse tangent of y plus c1 equals e to the x plus c2. Remember, from earlier, the integral of e to the x or e to the y or anything is just e to the x or e to the y. It's also something I don't think is specified, but it's all written out. So then you just take tangent to both sides. Once you first make it one constant on the right hand side, so you just have so it becomes y of x equals tangent e to the x plus c. Because here you take tangent on both sides, cancel out inverse tangent. I know that's something that you probably won't be tested on, but it's not uncommon to see on something you'd have time to work on, be able to look stuff up for. It's always good to, if you really can't integrate through U substitution or any type of method or even integration by parts, it's good to look for inverse, because there's occasionally an inverse tangent, a specific integral that becomes an inverse tangent function. So inverse tangent is the number one, like I think out of all of them. It gets reused occasionally. 5 here is y prime equals x times y plus y. So dy dx equals x times y plus y. This one we have to distribute out a y, so we get it by itself. It's something you have to trick it in times like this. So it's y times x plus 1. You can divide y to get them separate, so you have x and y on two different sides of the equation, then integrate them after we've separated the variables, as it's called. Continue on, and it's similar to before where we get a natural log of y. Remember your absolute values, because that's what the integral is, absolute value of y. But other than that, still, and you continue on, you split it up, e to the x squared over 2 times e to the x times e to the c. It's split up like that. And eventually e to the c becomes a constant, so it's y of x equals a times e to the x plus x squared over 2. So far we've had just general solutions, though. And this one again will be... So you put dy dx, again, like you always do that first. As soon as you can, you do that. Then you separate it. So we have this form. And the trick here is to split it up so you can easily split up x and y. This one is a little bit tricky, though. So after we've gotten in dy dx form, the one left-hand side, we have to make it so we can easily separate y. So we have y on one side, on the left-hand side, and x on the other side, on the right-hand side. We want that. Yeah, that's also not saying y is on the left-hand side and x is on the right-hand side, because of how it works. Generally speaking, at least from what I see. So we rearrange it, this expression, so it's y to the ex plus y minus 2 e to the x minus 2, so we can, split up a little bit. So we have distribute out a y and distribute out negative 2 from this, so we have y times e to the x plus 1 minus 2 times e to the x plus 1. Then we can further simplify down, like make two, so we have two binomials. We have e to the x plus 1 distributed out, and we have y minus 2. It's a weird use of the distributive property at first glance, but it works out. And now you can, of course, divide by y minus 2 on each side, and so you separate the variables. Then you integrate, and we have to do the first use of u substitution so far. So when you're trying to do this, the proper way, you have to do u substitution. So u equals y minus 2. That means that du is dy, because it's just derivative of y minus 2 is just 1 dy. So dy equals du. And we have u equals y minus 2, so we get integral of du over u for this. That's what integral dy over y minus 2 is. We get ln u plus c1, and the absolute value of y minus 2 as a natural log of that, plus c1. And that's equal to e to the x plus 1's derivative is just e to the x plus c2. E to the x is e to the x, 1 is x, and then you have the constant. And then we can simplify down, make it one constant on the right hand side, and we raise everything up, and eventually we get y minus 2 absolute value equal e to the c times e to the x plus x. Then we have y minus 2 because we get rid of the absolute value, and you have the constant a. So y of x equals 2 plus a times e raised to the power e to the x plus x. Yeah, you can have that sometimes. We have because remember, e is just a very specific number. That's one thing you have to remember. It's not like a variable. It's a specific number. The natural base, or whatever the proper name is called, but no, e is an actual number. It's an exact number on a calculator produces. No, it makes sense. But it turns out it's very common. So y prime equals x over y plus 2. You do dy dx. And we can easily separate this time. The difference is that we have integral y plus 2 dy equals integral x dx. So we get y squared over 2 plus 2y plus c1 equals x squared over 2 plus c2, and we make it one constant, of course, but we have a saying, well, we multiply by 2 to simplify out the fractions, to give a fraction. So we have y squared plus 4y equal, you multiply everything by 2, we get, and then it's equal to x squared plus c. Yeah, we can see in here. So c2 minus c1 is c3, and then c3 times 2 is just another constant. Anything multiplied by a constant, which it's been not shown exactly, but that's what happens quite often in a lot of, as well, differential equations. You often have things multiplied in, and when we do, that's part of when you do integrals sometimes. It's just something assumed. But a constant times a constant is a constant as well, you know, so nothing to get crazy about right now. So we have this expression, and we can write this as the quadratic equation in standard form of it. So y squared plus 4y minus this expression x squared plus c is equal to 0. And we solve for y, and we get an explicit solution after doing the quadratic equation. Y of x equals negative 2 plus or minus square root of x squared plus d, and d being a constant. Because of and all the math here is how you do it. Because we have negative b, so negative 4 from that. We have in the denominator, real quick, we have the 2a, so 2 times 1, because a is 1 here. B is 4, and c is equal to x squared plus c. C is a capital, you know, as a constant, but that's what it is. It's quadratic formula. So you have b squared here minus 4ac, so a is 1, and then c is negative x squared plus c. Remember that negative because it's negative x squared plus c. So you multiply that. You get the negative becomes a positive 4 times x squared plus c. And what we can do is we can divide out 4 from the, because you have 4 times 4 plus x squared plus c. Because 16 plus 4 times that, you can divide out a 4 and make it simpler. Becomes, you know. And then the 4 can be taken out of the square root. So you get negative 4 plus or minus 2 in the radical, and then you have the square root of 2, is divided by 2. So that cancels out the denominator. You get negative 2 plus or minus square root of, well, you have 4 plus x squared plus c, but you can let d, another constant, equal 4 plus c, so it's x squared plus d. And that's an explicit solution. That's what it looks like. That's what they mean by possibly getting one, and it only happens in these types of circumstances when you're given something like that. Oh. So number 8, it's y prime equals x times y divided by x minus 1. dy dx equals x times y divided by x minus 1. So we can just divide out y, and we get integrals. So dy over y integral and x over x minus 1 dx. And I put it in blue, of course, all the work for x. Hope you can see that fine. And that's what I did in blue. So, but dy over y, the integral of that is very simple. It's just ln absolute value of y plus c1. So I did u substitution. U equals x minus 1, and then you have du equals dx. And oh, but we have to do another trick. We have to do x equals u plus 1 as well. So we let x equal u plus 1. So we have integral of x over x minus 1 dx. That's equal to integral of u plus 1 divided by, so u is equal to x minus 1, so it's u du. That's the trick we used. We used a very, not as common trick. U substitution is a much more common trick. And remember, this trick, from my experience, is used as a way to avoid having to memorize tables of integrals for all these specific situations like this. So it's good to do it this way. So, and then we separate the integral into integral u over u, because it's u plus 1 divided by u, so that's u over u du, plus the integral of 1 over u du. So we have integral of du, pretty much because it cancels out just the 1, so it's 1 du, plus integral of 1 over u du. So we get u plus ln u of the values plus c2. Then we plug in the u value, so it's x minus 1 plus ln of x minus 1 plus c2. Of the values included, of course, in x minus 1. So get this expression, and I think I've talked to enough of this, so just continue on. You raise it to the power again after you get your one constant, and then again you get another constant out of it, eventually with e to the c. And continue, but oh wait, this summing. So c1, c2 are constants, but so is minus 1, so that gets eliminated here into c. It's all absorbed into it. That's why you get rid of that minus 1. Then later on, yeah, it gets simplified. Yeah, we can do e to the x times e to the ln x minus 1. And then ln, so e to that power, you get times x minus 1. So really, yeah, you eliminate that by the exponential being raised. So it's y of x equals a times the absolute value x minus 1 times e to the x. That's the process. These are very detailed because it's a lot of old calculus and algebra involved in figuring these out somewhat. So it should help. So it's good review to do all these. Go with them. X squared y prime equals y ln y minus y prime. So before we do any dy dx, this is one where I wanted to like simplify it down, like get it into position. So yeah, so first you add y prime onto both sides, because we really want y prime to be, yeah, we need one form of it, that's what we first have to do. So x squared y prime plus y prime equals y ln y. So that's x squared plus 1 times y prime, basically. You can distribute out the y, we basically distribute out y prime. Then we convert that to dy dx, and then we can separate the variables and solve the two integrals. As before. This time, 1 over x squared plus 1 dx is one of the integrals, and that's just inverse tangent x plus c1. So one of the, the constants. dy divided by, integral of dy over y ln y. Well, we have to do u substitution. We pick ln y here, because you usually pick the more complicated part. They can feel like and you have to make sure you can eliminate stuff. So you get everything in terms of u and, foot. So we get du equals 1 over y dy, and that means that y du equals dy. So we plug in and we get y du over y times u, and the y's cancel out, and you get integral du over u, simplifies down to the natural log of the absolute value of the natural log of y plus c2. Yeah, I know it sounds weird, but continues on. You have your constants, of course, get eliminated into 1. Then you raise it to a power, and we have the absolute value of ln y equals e to the c. Yeah. So we can eliminate the absolute value again with this constant a times e. We have e raised to the tangent, inverse tangent x, like normal. We raise it to the e power, and we do again same thing to get rid of the ln y and make it just y. So we get e raised to a times e raised to tangent, the inverse tangent of x. Yeah. Interesting problem. And we can't separate that into, so because of how it is, it's multiplied together, a times e to the inverse tangent y x. That's the solution. Here's another one. We have xy prime minus y equals 2 times x squared times y. We have to solve this one. So we basically make it so y prime is on the left hand side. Pretty much as it can, separate it first. We added y to that side. We get x dy dx equals y times 2x squared plus 1. And we have to be able to separate the variables, so we did that work. Then we divide out y and divide x. So it's 2x squared plus 1 over x dx for one side and dy over y for the other side. At this point, the natural log of the absolute value of y plus c1 is one of those things. Then in pink, in hot pink, we have 2x squared plus 1 divided by x. So we do a trick similar to, you've seen this maybe once a little bit. It's not as common. We basically separate it, so it's 2x squared over x integral, just integral of that dx, plus integral 1 over x dx, and then we integrate them separately because it just becomes 2x, basically integral 2x dx plus integral 1 over x dx because we simplified. Then we get for 2x it becomes 2x squared over 2, and 2's cancel out, and natural log of x in the constant, of course. So it's x squared plus ln absolute value x plus c2. And we combine, we go back, we use these two integrals together. You got, like, the work for these are separated by the coloring's just to separate the work. So when we get back, you know where each of them came from, the left and right side. And in the end, we have ln y absolute value equal x squared plus ln absolute value x plus c. You cancel out eventually, the same thing as before. Yeah, we have e to the ln x, so it becomes just absolute value x again. It's really just variations of the same tricks by this point, because I've shown multiple examples, an example of each. Oh, here's a quick one, because there's not really anything, you would never be expected to get an explicit solution from this. There's probably a way, using some somewhat more complicated algebras than the average person would have on hand. Just off the top of the head, they might not, there's some algebra that probably works with this, with y4, but we have y cubed times y prime equals x plus 2y prime. The solution we're left with ends pretty early because of this, but we can subtract 2y prime from both sides. Then we distribute out y prime, so that's y prime times y cubed minus 2 equals x. We get dy dx, we put in the variables thing. So it's y cubed minus 2 dy equals x dx, and we have integrals. So it's y to the fourth divided by 4 minus 2y. It's normal integration steps. Squared over 2. And you just can't do much further. That's our answer. Like, that's like one of the forms you have to leave it at. Can't really do much. And now this one is of this type. We have y prime equals 2xy plus 2x divided by x squared minus 1. So simplify out a little bit, we can distribute out y plus 1. Well, we distribute out the 2x, here, really. So it's y plus 1 times 2x divided by x squared minus 1. When the math starts, you have your separation of variables. You divide y plus 1 out from both sides. So we have integral of dy over y plus 1 and integral of 2x divided by x squared minus 1. So the trick here, we'll first do the blue, which is dy over y plus 1. You do u substitution. If you're honest, it's ln y plus 1 plus c1. It's clear. And we'll do u substitution, but with v, for distinguish it for 2x over x squared minus 1. Same, we've done this before. But yeah, you can see it's a very similar process for both of them. Then you simplify down. But the thing is, for this one, since they both have natural logs absolute values, I found it best to subtract, so we get it in terms, you just have everything equal to c, constant c. Then we basically simplify down the ln of the absolute value of y plus 1 divided by x squared minus 1, all absolute value, because we can do that with how it's situated. And this way we'll eliminate the absolute value in the end, because we get e to the c from the right hand side, and we have absolute value of y plus 1 over x squared minus 1 on this side. And we can just eliminate that and get the constant a, which is positive or negative e to the c. Then we simplify from there. You multiply by x squared minus 1, and then you subtract 1. Yep. So y of x equals a times x squared minus 1 minus 1. So in these next several ones, we determine exact solution of the initial value problem, and we have to indicate interval of existence as well after we find the solution. And it's an exact solution this time because it's for the initial value given, initial conditions given, however you want to put it. So y prime equals y divided by x, and we have y of 1 equals negative 2. dy dx equals y divided by x, and then you do separation variables. You've seen this one before, basically. Oh, this is just like the last one, though. That's why I also want to show it. So ln y minus ln x steps the values, so it gets canceled out in a very similar way, and you get y equals a times x. So y of x equals a times x. That's your general solution right here. Then we plug in, we have y of 1 equals negative 2, so y of 1 equals negative 2. So negative 2 is equal to a times 1, a equals negative 2. Very simple because x is 1 here. So y of x equals 1, basically. So y of x equals negative 2 times x. It's a very simple solution, and therefore the interval of existence is simple to talk about. The y dx is equal to yx. That's where we're going to look for one thing that doesn't work. So x cannot equal 0. So that means that is 0 to infinity. It has to be greater than 0, basically. Because we have to include x equals 1. So we'll take the positive spectrum, positive numbers. All the positive numbers instead of the negative side. Because it has to include the point y of 1 equals negative 2. So the point is the two coordinates. So this to include the point x equals 1, y equals negative 2. And this involves the x values. So yeah. Okay, now it's time for a little bit longer one. So y prime equals negative 2 plus 1 plus y squared divided by y, and y of 0 equals 1. Very common to have an initial value problem. Use the variable equal to 0 as part of it, like the one that's the input, the independent variable, we call it. Whether it be x or t or any other ones. So dy dt you do. So it is set up from the beginning like that. So what we do is basically we're multiplying by y and dividing by 1 plus y squared to get it separated. So we have integral negative 2t dt is equal to negative 2t. It's very quick to do that one. It's a simple one. In right here, negative t squared plus c1. So in brown we have u substitution for 1 plus y squared. And you kind of, after doing enough of these, you get a feel for when u substitution how it will work. No. Generally, it's like your number one resort, though, in many cases. When you can't just right away integrate, you have to do u substitution of a sort. And then integration by parts, of course, is the second option. Generally, you'll find yourself looking at. That's later, we'll see. But no, like u substitution is your number one option if you really don't know on a test, especially. Try. Just have to find the right thing. It's usually obvious enough like this when you have done enough. So 1 plus y squared, and then you go through the process. I think it's neatly detailed. So 1/2 ln 1 plus y squared plus c2. And we simplify out. Right, c3 is c1 minus c2. In this case, I use that. Then I multiplied by 1, I multiplied everything by 2 to get rid of that 1/2. So it's ln 1 plus y squared, so equal negative 2t squared plus c. And c is, in our terms of progression, it's 2 times c3. It's constant. These are all constants for those. 1 plus y squared. So if we just go on, we basically eliminated it, the natural log, like before. Then we eliminate the absolute value, like many times before. Oh, here's the problem. We have y squared eventually equal to this expression, so we take the square root. We get y at t equals square root of a times e to the negative 2t squared minus 1. Then we do initial condition, y of 0 equals 1, which is equal to the square root of a times e 0 minus 1. E to the 0 is 1, so this is square root of a minus 1. So we basically squared both parts as well while plugging in. So it becomes a minus 1 equals 1. So a equals 2. Then you have your general solution, well, exact solution. General solution is here with a in it, and then exact solution just has terms of y and t. But we have to do one more. Interval of existence. And you look for where there's a problem in the original differential equation, and also in generally the solution is where it appears more often. Exact solution here. So this has to be positive. It has to be positive or equal to 0. It has to be greater than or equal to 0 because it's a square root. And what? So we solve for t when you have 2 times e to the negative 2t squared minus 1 greater than or equal to 0. Basically becomes, we have to take natural log eventually, so it's natural log 1/2 eventually. So we get negative 2t squared greater than or equal to ln 1/2. Well, it becomes ln 1 minus ln 2. And the logarithm, but regardless if it's a natural log or just some other log with a base. Because remember, natural log is log base e. So it's 0. The natural log of 1 is 0. The logarithm of 1 is always going to be 0. So that's a property. So we have negative 2t squared greater than or equal to negative ln 2 basically. We can divide by negative 2, and we have to swap the sign to t, so it's t squared less than or equal to 1/2 ln 2. This negative 1 divided by negative 2 is 1/2, just positive 1/2. Then we have t squared is less than or equal to ln 2. We put the 1/2 power, so it's t squared less than or equal to ln square root of 2. Then we have the absolute value of t less than or equal to the square root of this. Because we take the square root, we have to consider both positive and negative. So if the absolute value of t is less than or equal to square root of ln square root of 2, the negative square root of ln square root of 2 will be less than or equal to t, which is less than or equal to the positive square root of ln square root of 2. And we get this as our interval. But the reason is, like, positively it's t, and negatively you swap the sign when you divide by negative. So that's why it flips like that. So it's greater than or equal to the negative, but that's what you get, the negative. It's greater than or equal to that, but it's less than or equal to the positive. Remember. So the interval of existence is written as this with square brackets because of the equal sign being included. Okay, we're almost done with this area. And you should be an expert on these with all this. Paying attention. So y prime equals sine of x divided by y, and we have y of pi halves equals 1. So we have to solve. We end up with integral y dy because it's equal to integral sine x dx. It's a very quick separation. All fits here. So we do a simple y squared over 2 plus c1. It's equal to integral of sine is just negative cosine x. And of course we get rid of the constant, so it's just one constant, c3. We multiply by 2 to get rid of that 2, so it's y squared equal to negative 2 cosine x plus c, and then we take the square root to get y of x. So y of x is equal to square root of negative 2 cosine x plus c. And I mean, it's implied it's positive, and I think you don't have to always explicitly state it's plus or minus. I think it doesn't hurt to do it when you add the square root in, but that's what it is. But we're more concerned with the interval of existence, which will involve what's under here. We'll see that. So first let's actually get a solution for this. So the exact solution now, because we have a general right here, a general solution, we have to get rid of this constant. So y pi halves is equal to 1. So that means that we have negative 2 so it's equal, so 1 is equal to the square root of negative 2 cosine pi halves plus c. We square both to get rid of sides to get rid of that square root, so it's 1 equals negative 2 cosine pi halves plus c. Cosine pi halves is 0. So negative 2 times 0 is 0. So we eventually get just c equals 1. So y of x, we can just 1 is here, so it's 1 minus 2 cosine x. That's what us, square root of 1 minus 2 cosine x. So now 1 minus 2 cosine of x must be greater than 0 for the square root to work. I think it argues greater than or equal to, but I wrote down greater than. I think it might be greater than or equal to because it can have 0. 1 minus 2 cosine x could equal 0 and it'd be fine, the square root, but I mean the basic idea is, the principle is still right, the idea of like, so ignore that really. I mean, an equals, you can add in an equal sign there and it'll change just a little. But it's going to be the same. So 1 greater, so we have 2 cosine x. Then 2 cosine x is less than 1 because we switch it around. So 1 is, we add 2 cosine x both sides. 1 greater than 2 cosine x, and then we flip it around to have 2 cosine x less than 1. You could do that just because we want to solve for x. Then we divide by 2, so cosine x is less than 1/2. We take the inverse cosine, just get x by itself. So x is less than the inverse cosine of 1/2. Now we have to consider what we have, our initial value. What we're given is what an exact point in it will be. So x can be less than pi thirds, 5 pi thirds, 7 pi thirds, etc. Because of how, so the interval between two such values is the interval of existence, and it must include x equals pi halves. So let's start from pi third, the 5 pi thirds. So it has to be in this area, and pi halves is between those two values. We can't include what's above them, like this thing. From 5 pi thirds to 7 pi halves is not going to be included, so because it does not exist, the solution to that. So it's this little region here of the I drew out the cosine curve in general. So its interval of existence is pi thirds to 5 pi thirds. So we have y prime equals x plus y of 0 equals 0. So e to the x plus y can be turned into e to the x times e to the y, and then you can easily split them up. When you have this just e to the y, but it's in the denominator, when you integrate, you have to make it e to the negative y. We have e to the x dx, of course, for the other side. So e to the negative y dy integrated. You basically do u substitution. U equals negative y. We have du equals negative dy, because it's negative 1 basically. The derivative of negative y is negative 1 dy. So you go on with that, and you have dy equals negative du. So the integral of e to negative y dy eventually you can see is negative e to the negative y plus c1. Because when you integrate e to the u or e to the x just by itself, it becomes e to the u or e to the x. When you do it with u substitution, at least, it's like that. When you simplify down. But you have the negative here, negative e to negative y plus c1. Okay, so then we have the right hand side, which is e to the x plus c2, and you simplify down. Negative e, negative y. Negative e to the negative y power equals e to the x plus c3. Right here. And then we divide by negative 1, so we have negative e to the x minus c3. So it's basically, I kept it as minus c3 here for a moment. and you can take the natural log and you get natural log of negative e to the x minus c3. Then I simplified it down, so it's y equals negative natural log of negative e to the x plus big C. C alone. So we have the constant c here. So y of x equals negative ln the negative natural log of c minus e to the x. Rewriting it several ways here. So y of 0 equals 0. That means that we have that, so 0 is equal to negative ln of c minus e to 0. So if 0 equals, because we can divide by negative 1, so it's 0 equals ln of c minus 1, because it's e to the 0 is 1. So we have e to the 0, because we raise it to e power to get rid of natural log, so equals c minus 1. So 1 equals c minus 1, so you have c equals 2, because you add 1 both sides, get c equals 2. So y of x equals negative ln 2 minus e to the x becomes. And 2 minus e to the x, it absolutely has to be positive. Unlike a square root, you can't have natural log of 0 or negative. So it has to, this is absolutely a positive number. So greater than 0. So you add e to the x, so it's 2 greater than e to the x, and we have to flip it around because we want to solve for x, so it's e to the x less than 2. Take the natural log of both sides, and you get x less than ln 2. So y of x equals negative ln 2 minus e to the x we have as a solution, and interval of existence is negative infinity to ln 2. And we figure that because our condition is it has to be less than ln 2. Right. That's the same. That's the only restriction on it. So y prime equals 1 plus y squared, y of 0 equals 1. Again, you can tell that trying to make those exponentials can't be simplified. So you can just quickly do dy dx equals 1 plus y squared. Yeah, when it just has y prime equals 1 plus y squared, you can assume x or t, I think, and it doesn't matter. You can assume, I generally like to assume x in a lot of cases, but it's not specified like that. But if you're not given information on it, anything is appropriate like that. But generally speaking, x and t are the main other variables that are involved with this kind of stuff, just as a note. So, but dy dx equals 1 plus y squared. I don't know if I had no one looked at before. So we divide by 1 plus y squared to get dy 1 plus y squared. So inverse tangent again of y plus, so we had this a couple times before. So yep. We just have the integral of 1 dx basically is, so it's just x plus c2. So we can simplify down. We take the tangent of both sides to get rid of inverse tangent, so it's y of x equals tangent of x plus c. This will be interesting. Y of 0 equals 1, so 1 equals tangent of d plus c, or 0. Oh, that's a 0. Almost looks like a letter, but it's 0 plus c because x is 0 here. So it means that 1 equals tangent of c, and c is equal, then we take the inverse tangent of both sides to get the inverse tangent of 1. So c is equal, we assume c is equal to pi fourths, because that's what the inverse tangent of 1 gives us. So y of x equals tangent of x plus pi fourths. That's our exact solution. Tangent of x continuous on interval negative pi halves to pi halves. This is like a rule. When we're considering the tangent function where it's continuous, it has like a discontinuity at pi halves and negative pi halves. So we have negative pi halves less than x plus pi fourths less than pi halves. If you want to see the process of figuring this out here. So we just subtract pi fourths to get the range for x. So negative 3 pi fourths and pi fourths. So it's in between those. So interval of existence is equal to negative 3 pi fourths and pi fourths. I think it's in between those two. That's from negative 3 pi fourths to 4 pi fourths. Yeah. Oh. We can close that. Okay. One more just like this, and we have two interesting examples. Let's start using separable equations. So y prime equals x divided by 1 plus 2y, and y of negative 1 equals 0. So dy dx equals x divided by 1 plus 2y. Is what you do when you do it. So you separate that 1 plus 2y on the left hand side, x dx, you know. Again, just follow this. We have simplification here for the... Oh, we do have to, it's more algebra at points, like simplifying down multiple. We do have two more. Yeah, we multiply, we get them so that's all like, there's no fractions. So 2y squared plus 2y minus... Oh, I see, yeah, we have to solve a quadratic, I see. Make sure because it's all bunched together at the top because it's quick. Yeah, basically this is our c term is negative x squared plus 2 times c3, or it becomes just c, like big C here, x squared plus c. So we did one like this before, so quickly just go through all the process and you should get y of x equals that. Oh, I see. Oh, that's how we leave it. Yeah, we leave it as a solution at. So y of x equals negative 1 plus or minus the square root of 2x squared plus d divided by 2, and then we're going to solve for d by using the initial value here. So y of negative 1 equals 0. So 0 is equal to negative 1 plus or minus square root of 2 times negative 1 squared plus d. Continue filling it in. This is very similar to that process we used to have. So it's like, so we solve for d because we have 0 on one end, equal sign. Yeah, we can multiply by 2, so that gets rid of the denominator. Then we add 1 so just plus or minus square root of 2 plus d equals 1. We can square both sides to get 2 plus d equals 1, so subtract 2 and you get d equals negative 1. So exact solution is y of x equals negative 1 plus or minus square root of 2x squared minus 1 all divided by 2. And 2x squared minus 1 has to be greater than or equal to 0 when we consider what values are acceptable for x. So 2x squared is greater than or equal to 1. So x squared is greater than or equal to 1/2. Then we take the square root of both sides, so we have the concern was the absolute value of x is greater than or equal to the square root of 1/2. And we can simplify, so it's 1 divided by square root of 2. What this thing is. So x is less than or equal to negative 1 square root of 2, or x is greater than or equal to 1 over square root of 2. And that's a similar trick to several problems before, where when you basically the negative is the flipped sign, so it has to be less than or equal to that. So basically x is less than or equal to negative 1 over square root of 2, or x is greater than or equal to 1 over square root of 2. We have to consider what our initial value is. It's negative 1, so x equals negative 1 has to occur. So we go from negative infinity to negative 1 over square root of 2. Because negative 1 divided by square root of 2 is it's greater than negative 1. So it has to be in that existence. Because the other part is, otherwise it'd be 1 over square root of 2 to infinity, and that does not count it. That definitely does not count it. That's an interesting problem here, but that's basically what you have to consider with these interval of existence problems and all that. So now some word problems. Tritium, which is H was a 3 up here, is an isotope of hydrogen that's sometimes used as a biochemical tracer. Suppose that 100 milligrams of tritium decays to 80 milligrams in 4 hours. So that's 80 milligrams in 4 hours, determine the half-life of tritium. So we're going to look at the work behind this because otherwise it's a quick answer if you know. But it's good to go over the process. So we have n prime equals negative lambda n. That's like the general thing for this type of exponential function with differential equations. So you have dn dt, it's a separable one, equals negative lambda n. Exponential decay follows this often enough. It's a good approximation, at least in many situations, to get an idea. So, negative lambda is a constant unique. It's unique to an element, basically, in this case. Like, think of it, tritium. It's unique to tritium. Just to not get into the chemistry too much of it, but basically that's the idea. So it's a unique thing, so it's related to it. And we do have to solve for lambda, as you can see ahead, before we can solve what's asked for. So, but we solve this differential equation to get an equation in terms of n, basically. So dn dt equals negative lambda n. So we can separate the parts, so it's integral dn over n equals integral negative lambda dt. So we get ln, absolute value of n, plus c1 equals negative lambda t, because negative lambda dt just becomes negative lambda t, plus c2, so ln, absolute value of n, equals negative lambda t plus c, and we process like before, we get n equals a times e to the negative lambda t. Now what does a mean? Well, t equals 0 implies that n0 equals a, because e to the negative lambda t will be e to the 0, which is 1. Because 0 times lambda will be, negative lambda will be 0, so we get e to the 1. I mean, e to the 0 is 1, so it's n equals a. So especially in a problem like this, in like science especially, it's definitely referred to this at times, but even in math we can call this n0. Basically, that's what I put here. So when t equals 0, you put a 0 under it. So that's why n0 I wrote here as well equals a. So it implies that n equals n0, or n naught, times e to the negative lambda t. Because at time t equals 0, the amount present is n0. And that's it. So when you before any time has occurred, it's the initial amount, basically. N0 is what you begin with, and n is the amount at any time t. Otherwise known as n of t and all that. That's why it's called it's a real-world application that's interesting. So, in the solve for lambda, we do divide by n0. You take the natural log of both sides. So we just get negative lambda t, and then lambda equals negative ln n divided by n0 divided by t. We can just leave it like that. And we have 100 milligrams of tritium decays to 80 milligrams in 4 hours. So t equals 4. We know t equals 4, and in this case we can do n equals 80, because that's a time of 4 hours, and n0 equals 100. So 100 milligrams and 80 milligrams. So we plug all that in. Make sure you keep the signs right. So it's negative ln of 80 divided by 100. That'll be a positive number divided by 4 hours. So lambda equals positive. That's why I put a plus there. Positive 0.0558 hour to the negative 1 power. It's like per hour. That much decay in an hour. Or something to that effect. So now we're looking for determining the half-life. In half-life, there's a formula you can always look up, but like if you ever did not know it, you could figure it out this way with this idea in mind. This is like the derivations in red. So let n equal 1/2 of the original amount, which is what a half-life is. It's a time to get the half of what was originally there, present. So we have 1/2 n0 equals n0 times e to negative lambda t. You divide out n0. Here you have, see? Divide them out. So we have e to the negative lambda t equals positive 1/2. Okay? So negative lambda t is equal to ln 1/2. Then you have t 1/2. You can put it as t 1/2 if you really want to, and I did that then. And t 1/2 equals negative natural log of 1/2 divided by lambda. So in this case, we have t 1/2 equals negative, well, then we add negative ln1 plus ln2, because really it's negative 1 times this natural log, which is ln1 minus ln2. We want to split up and simplify for future reference so you have an idea what you're looking for. It becomes just positive ln2 divided by lambda. So the half-life is ln2, so natural log of 2 divided by lambda. So all you have to know is lambda, constant lambda, know this. So T1/2 equals ln2 divided by 0.0558 hours to -1. And then we flip that, so the unit is 12.42 hours. So the half-life is 12.42 hours. One more problem like that. So isotope iodine 131 is used to destroy tissue in an overactive thyroid gland. It has a half-life of 8.04 days. If a hospital receives a shipment of 500 milligrams of I-131, how much of the isotope will be left after 20 days? Now, we're not going to do any of the math too much. We're going to just plug in mainly. But so n equals n0 times e to the negative lambda t. You already saw how to get that. T1/2 is 8.04 days, because we get given that. Initial amount 500 milligrams. We know we want the time in 20 days, so T1/2 equals ln2 over lambda. So we plug in T1/2, and we figure out for lambda, so we multiply by lambda and divide by 8.04. So ln2 divided by 8.04 days will be lambda. You get 0.0862 reciprocal. Reciprocal days is one way of saying that. Because you want to keep units just because they cancel out then and it looks nice. I think at times nice to show. But that's how this works. And then you just plug in the n equals n0 times e to the negative lambda t, because we have lambda, we have t, and we have n0. So 500 milligrams times e to the negative 0.0862 days, well, reciprocal days, times 20 days, so days cancel out. So it's 500 milligrams times what this amounts to, which is the unit listing 0.17835, so it becomes, and then it's 89.18 milligrams. So 89.18 milligrams of isotope is left after 20 days. Approximately. Because there's some rounding involved, of course. But that's about what we left. And that's it.